marginal DAG node is equivalent to another DAG.
Thank you very much. And yeah, thank you to the organizers, Thomas and Frederick, for inviting me to present this. So this is a sort of slightly esoteric talk in the sense that I think if you're not interested in marginal DAG models, then you might not find it as interesting as I do. But my aim was to sort of help to try and bridge a few gaps by introducing some concepts that I use in the proof that might be of interest to quantum physicists and statisticians who haven't come across them before. So let me just briefly introduce the problem. So hopefully by now you've got the idea about what a DAG model is. So we have here a graph over 4 variables, and one of them is assumed to be latent, this H here. And the question we might ask is whether there is some other directed acyclic graph model which is distributionally equivalent to this one over the 3 observed variables, X, Y, and Z. And in this case, it's very easy to see that there is. We can just have the edge point from X to Y and just set H to be equal to X. So X will tell X what it's supposed to do, and it will give Y exactly the information it needs to respond to X. And therefore, these 2 models are identical. On the other hand, this is another model which is known very well not to be equivalent to a DAG at the first level, just because the conditional independencies can't be explained by any DAG model, right? So you can't have W jointly independent of Y and Z jointly independent of W and X, and only those independencies in any DAG model. So this is sort of a contrast between some models which can be represented as DAGs without any hidden variables and some which cannot. So the question is, which models can be represented as DAGs without any hidden variables and which can't? Okay, so the background on studying this problem is very long, so I won't go into the details. So the important thing is, because we're often using these DAGs as causal models, we're not going to want to assume that we have observed everything. It's very likely we will not. So you need to posit the possibility of there being latent variables. And that's why we consider these models. And there's the problem of finding the constraints in these models has a long history. So several of the people in this list are in the room. So Jamie, Thomas, and Jin are all here. And there's a sort of even longer, actually, literature on finding inequality constraints, because Bell did this before anyone had come up with the idea of a DAG model. So he didn't draw this picture. It's sort of been imposed afterwards. And obviously this was followed up by Closer et al., who developed the CHSH inequality. And then independently of that, Pearl introduced the instrumental inequality, which gives an inequality over the observed variables on this graph here, which is expanded by Bonnet using computational algebra. And then there's been a whole series of other papers on this topic, including many that aren't mentioned here and have already been presented. And then most recently, of course, Ellie, Rob, and Tobias Fritz have a paper on what's called the inflation technique, and it was shown to be complete in the sense that any distribution which is not in the model can be refuted if you take a large enough inflation and look at the constraints. So I should just emphasize that all the hidden variables I use will be classical, so there's nothing excitingly quantum going on. Okay, so we understand quite a lot about the marginal DAG model because of all those papers. So we know that there are 3 kinds of constraints you can get on a model where you don't make any assumption about what the hidden variables are. So the first are conditional independencies, and you can only observe them if there's a conditional independence in the original model where all the variables are observed. And then you get these things called nested conditional independencies, which I'll show you in a second, which are also now quite well understood. And we know that, for example, if you combine just these 2 constraints, that defines the model up to its dimension. Right? So we know there's no other equality constraints beyond these 2, at least if all the observed variables are discrete. And then on top of this, we get the inequalities, which I think is by far the least well understood of these 3 possibilities. And so let me give you a quick example. So this graph has all three kinds of constraints. So first of all, you might notice that W is d-separated from T. So I'm not going to define d-separation because Beata did it very nicely earlier. But the point is there's two paths from W to T, one of which goes through X and on which X is a non-collider. The other which goes through X as a collider, but then has Y as a collider. So as long as we don't condition on Y, then that path will also be blocked. And therefore we get this d-separation relation here. Then there's also a nested constraint, because if we do this identifiable intervention, so we sort of get rid of this edge by dividing by this observable conditional distribution, we get this new model. And now you notice that W is now d-separated from Y because we've deleted this path. And before it wasn't, right? Because if I condition on, if I don't condition on either X or T, then this path's open. But if I do condition on X or T, then I'm going to open up this path here, or the collider X. Okay, so this was not visible before, but now we see there is a constraint, which corresponds to the fact there's no edge from W to Y. And then finally, you can also see that this is now the Bell graph. So we get the inequality that's associated with that, the CHSH, or Tyrolson's inequality, if it's a quantum variable. Okay, and the aim today is to show this main result, which is that if you have a DAG over latent and observed variables, and then you marginalize out the latent variables, then the model that you get, which we call the marginal model, which I'll define formally in a sec, is the same as the marginal model for some DAG over just the observed variables, if and only if there are no non-trivial inequality constraints implied by G. So what do I mean by non-trivial? Obviously, probabilities have to be non-negative. So that is a trivial inequality. But there are also trivial inequalities you get just by considering marginals of DAGs, right? So if you can observe a marginal and that gives you some inequalities, then they don't count. So it has to be some inequalities that are over and above what are directly implied by the equality constraints that you have. That's what I mean by a non-trivial inequality. So why do we care about this question? Well, so originally, Richard was asking me about when it's the case that an MDAG is distributionally equivalent to some DAG. And he was interested because in semi-parametric efficiency theory, it's very useful to know what the tangent space of a DAG is, of a model is. And if it's equivalent to a DAG, then that's really well understood. And then we had a conversation with Ellie, and he conjectured that basically that would be true if and only if there weren't any inequality constraints. And I was like, I can't believe I didn't think of this conjecture before, but thank you. And I will now try and prove this. And I believe that's what I've now done. So this is a completely new talk, so there may well be mistakes, and I'm very grateful if you were to point any out. Okay, any questions at this point? Okay, excellent. So hopefully this slide is slightly superfluous now. So a directed acyclic graph is just a graph with directed edges where there's no directed cycle. This is an example. And we say that a distribution is in the model for a DAG if each variable is a measurable function of its parents, i.e. the things that are pointing into it, and some independent noise. And it's equivalent to say that these independencies hold for each of the vertices in the graph. Okay, an MDAG is obtained from a DAG by marginalizing. So we use an operation called latent projection, which again, I'm not going to define, but it does something like this. So if you start with this graph over on the left, where now I've made the H's be latent, then what I'm going to do is if I have a latent like H1 here, and it's got a directed path to say K observed vertices, then I'm going to put in a K hyperedge between those guys. So I replace the latent with this sort of triple hyperedge here. And then if there's a directed path that goes through a latent, so for example, T H2 to Z, I'm going to replace that with just a directed edge that's observable. Okay, and this one could show preserves the model precisely, right? So there's no difference between the marginal model over this there's no difference between the margin of the model over this graph and the marginal model over this MDAG. Yes.
You're allowing the state spaces to be arbitrary.
Yeah. So just to repeat, yeah, so we are allowing the state spaces of H1, H2, and H3 to be arbitrary. So it's not true if we restrict those to have a finite cardinality necessarily. Okay, and we represent this by what we call an MDAG. So an MDAG is a DAG, which is the blue edges here. And then also we have a simplicial complex, which represents the latent structure. So the idea is here, I've just represented the maximal facets of that bidirected simplicial complex on the graph. So they are X, Y, Z, and ZW. And of course, T also has to be in the simplicial complex, but I'm not going to draw that on because it's not interesting, right? If that's the only variable in a facet. Okay. Yeah.
Can you just clarify real quick exactly what assumptions you're making on the hidden variables and the observed variables? Are they continuous, discrete, anything about the state spaces?
So yes, good question. So the observed variables are discrete, finite discrete, and the hidden variables are arbitrary, although one can show that they can also be assumed to be finite and discrete, thanks to various people's results. Right. Okay, and then we have this other. Is there another question? Yeah.
No, it's just really. Is there an obvious reason that's going to be simplex that I'm just not? And it's the first time I've ever seen it. You say it's a simplicial complex. Is it obvious why that'll have to be a simplex?
So simplicial complex is just a collection of sets where every subset of a set in the set is in the collection.
Okay.
So I'm just representing the maximal guys on the graph, but not singletons. Okay, and then we need another concept, which is what we call the canonical DAG. So given an MDAG, like this one here on the left that we just obtained, we can get the canonical DAG by just replacing any of these bidirected facets with an explicit latent variable with the same children. So you can see this graph here is not the same as the one we started with, because now T does not point into H2, for example, and H3 has just disappeared entirely. But this, again, has the same marginal model over the observed variables as this MDAG. And then, I mean, at this point, I think the definition of the marginal model is pretty obvious. It just means you take the MDAG, you form its canonical DAG, you look at the set of distributions that are Markov with respect to that DAG, and then you get rid of the unobserved variables, and that set is what we define as the marginal model. So a very simple example, if this is the MDAG, so we've just got a bidirected edge between X and Y, so it's very similar to the example I started with. This is just going to imply that there's a conditional independence, which you can read off as an M separation, which is essentially the same as D separation. And there are no other constraints because, again, I can just set the hidden variable to be Y, tell Y what to do, and X will then learn what Y is. Okay, any questions at that point? Excellent. Okay, so I'm just now going to outline the proof strategy. So in one way, it's obvious, right? We know there are no non-trivial inequalities in a DAG model because the definition is just made up of a set of equality constraints. So no work to do there. For the other direction, things are a little bit more technical. So the first thing we're going to do is show that if we take something called the maximal arid projection, which I'll define shortly, it will first of all preserve all the equality constraints. So it has the same nested model as the original graph, but it will increase the size of the model. So any inequalities might be removed. So why is that okay? Well, let's think about this. So if we have a counterexample to our conjecture and we take its maximal arid projection, then that must also be a counterexample, because if it's a counterexample, it doesn't have any inequalities, then its maximal arid projection will also not have any inequalities, and it will be distributionally equivalent to the graph we started with. So there's no point in looking at graphs that are not both maximal and arid. Okay. Then we'll show that if there's a non-trivial nested constraint, then that's going to imply there's non-trivial inequality. Okay, and then this is the bit which I think can be finessed if we understand sort of the equivalence class of maximal arid graphs better. which was something we're working on right now. So then we know that we can just take the maximal ancestral projection. So this is analogous to the arid projection, but it's older. And it preserves precisely the conditional independence structure, which is, we know, is all the inequalities that can be left if we know there are no nested constraints. Okay, and then we'll show that this also only removes inequalities and doesn't potentially introduce any. And then finally, we'll show that if you have a model that necessarily has a bidirected edge in it, then it's not equivalent to a DAG, and it will also induce a non-trivial inequality. Yes, this question there behind the post.
So does this mean that on the way to proving your main result, which is about inequalities, you've also characterized which ADMGs or DAGs graphically somehow?
No.
Or not? No. Okay. Interesting.
I have not done that. So I think that's much harder.
Okay, got it.
Right. So this is a proposition. I don't expect you to read all this, but it's going to be useful for proving that you don't introduce any inequalities when you take the maximal arid projection or the maximal ancestral projection. And this is sort of originally from a paper of mine in 2016 that's since been extended by Ellie and Marina Antonelli, but not yet published, I think. Is that right? Yeah. So basically, the idea is if you have a bidirected facet like this one here, W, X, Y, and Z, in some circumstances, you can split it into two smaller facets. So in this case, you can. And what you need is that the information that's sort of shared between the two bits that you're splitting up isn't helping you. Okay, and the reason it's not helping us in this case is that Y and Z can see W and X, and they can see all the parents of W and X, i.e. T and S as well. So this guy is not doing anything. And therefore, we don't need to share information, this hidden information between these two sets of vertices. So I can just replace it with a good old-fashioned bidirected edge between W and X and a separate edge between Y and Z. And these two models, these two marginal models, are exactly the same. Okay. So then, sorry about this, Miguel, I'm going to need another definition. So the intrinsic closure of a set is something I'm going to need to define. So intrinsic closure is just obtained by alternating between two things. So we take the set and we look in the graph at all its ancestors. And then we take the subgraph of that, of just the ancestors. And then we alternate, so then we take the district, which is anything you can reach by one of these red paths. And then you do it again. So you then take the ancestors of that subgraph and then the district within that subgraph. And potentially this can go on, only removing one vertex at a time. But fortunately, there aren't many vertices in my graphs, so it won't take too long to go through. Right, so what's the intrinsic closure of Y, for example? We could start off by taking the ancestors. So in that case, that's going to get rid of Z because it's not an ancestor of Y. So we'll just sort of gray that out. Then we could look at the district, which you can see is just going to be X and T. So we get rid of W. And that's it, right? There's nothing else I can remove because X and T are both parents of Y and they're all in the same district. Okay, so the intrinsic closure of Y is the set X, T, and Y. And then a second example, we can consider the intrinsic closure of a pair. So let's suppose we want the intrinsic closure of Y and Z. Well, again, we could first restrict to the ancestors, but that's not going to do anything because everything is either an ancestor of Y or of Z. Then we could look at the district, and that will again get rid of W. But now again, we have to stop because everything is an ancestor still. So there's nothing to iterate. Okay, so the ancestral closure of YZ as a set is this set of 4 variables. Okay, and an MDAG is said to be arid if for every vertex, the intrinsic closure of that, just that vertex, is itself, right? So there's nothing which is connected to it by these nasty paths like this, where we can't sort of separate X and Y because there's a bow. It can be slightly more complicated than that, but that's, I think, a good way of thinking of it. So every singleton vertex needs to be an intrinsic set. So it's its own intrinsic closure. And we then say an arid graph is maximal if every pair of edges with no nested constraint between them is adjacent. So I'm not going to describe in detail when there is and is not a nested constraint, but we'll see an example in a second. So here on the left, we have a graph which is not arid. That's because the intrinsic closure of Y is Y and X. So it's just itself, but it is maximal because every pair of vertices is adjacent. On the other hand, this is a graph which is arid, but it's not maximal because, as we just saw, the intrinsic closure of Y and Z in this case is everything, and that is bidirected connected, which means there can be no nested constraint between Y and Z. So yeah, this is something called a dense inducing path, but I don't wish to introduce any more definitions than I have to. Okay, so how do we get, we start with some MDAG. How do we get the maximal arid projection? So this is going to be a slightly different definition from the one that Thomas and Ilya probably know, but it is equivalent. So the first thing we do, we just take the graph and then we add directed edges, if we need to, from any vertex which is a parent of anything in the intrinsic closure into the vertex. And then we go through all the non-adjacent pairs and check whether or not the intrinsic closure of that pair is bidirected connected. And if it is, we add in a bidirected edge. And then finally, we go through and then remove any bidirected edges that are in bows, i.e. where there's already a directed edge. So if you have two edges between a vertex, you need to get rid of the bidirected one as the last step. Okay, so here's an example. So this is the same as the graph I was looking at, a sort of combination of the graph I was looking at earlier. So the first thing we need to do is note that the intrinsic closure of Y is YXT, which we calculated before, and therefore any parents of those guys need to also be directed into Y. So in this case, W is a parent of X, and therefore we need to add this directed edge here. Okay. Then we might notice that Y and Z have an intrinsic closure which is bidirected connected, so we need to add this bidirected edge down here. And then we've done the first two phases now. There's only one edge to add in each case. And then we need to remove any bidirected edges which are where there's already a directed edge. So we just get rid of that bidirected edge there. So we'll gray that out. And then this model is the maximal arid projection of this graph on the left. Okay, and then this is where that useful result comes in, because now we can see that, yeah.
Sorry, a quick question. Is it unique? So because,
Yes.
Okay.
It is. Yeah, so you can check in our paper that no matter what order you do things in, you always get the same result. Good. So that now this is where our useful proposition comes in, because when I remove this bidirected edge, you can see that the parents of X, which are W, is also a parent of Y, and X itself is a parent of Y. And the only other bidirected facet involving X has only T as a child, which is also a parent of Y. So there's nothing to worry about when we remove this edge. We will not introduce any new inequalities. Okay, so we know that taking the maximal arid projection won't change the nested constraints, but it might reduce the number of inequalities, but that's fine, because we know if G is a counterexample to result, then so is G dagger, the maximal ancestral projection of G. So in other words, we can just choose to consider only maximal arid graphs, and if there is a counterexample, which there isn't, then we know that we will find it in that set. Okay. So now, this is the bit that I would sort of suggest that we could probably avoid doing if we understood the sort of equivalence class of nested models a bit better, but we still don't. So for the moment, this is how to do it. So if there's a non-trivial nested constraint, that means that there's some vertex you can fix. So in this case, it's T, and a new M separation will appear. That's the definition. So this can only happen if the graph isn't ancestral, which means we have, in this case, we have this vertex Y. It has an ancestor X, but it's also joined to X by a single bidirected edge. So that's a graph which is not ancestral. And the point is then we can fix T, and a path that was open, conditional on Y before, becomes closed because there's no collider there anymore, right? Sorry, there is a collider, but it's no longer an ancestor of Y. So this means that W becomes deseparated from Y if you don't condition on anything. And basically, we can show that for any maximal arid graph with a non-trivial nested constraint, there is also a non-trivial inequality. So I think this is quite an interesting result because we've sort of known for a while that these maximal arid graphs have the same dimension as the marginal model, but we haven't known whether there are any that achieve the boundary. Okay, and we know now that if it has a nested constraint, then it doesn't achieve the boundary, and there is some gap. That may not be of interest to quantum physicists, but it sort of gives you different models that you can try, right? You can say, okay, well, maybe there's an inequality which is quantum violable in this set of inequalities. Okay, so a very sketch of why nested constraints will induce inequalities. So in order for there to be a nested constraint, you have to have two vertices that are in the same district. That's, in this case, that's X and Y, and some vertex that's in between them, which we'll call C, that you can fix. And it can't be in the same district as X and Y, otherwise it wouldn't be fixable. And then the point is that will induce some new M separation, and generically, it seems that you'll only get a completely new independence in one of these three cases. So here, I'm going to fix X given W. Here, I'm going to fix T given X. And here, I'm also going to fix X given W. So in this case, the two children of X, which I fixed, become independent given X. And so in general, they could be descendants. In this case, it's that this descendant of T becomes independent of a parent of X after we do the fixing. And in this case, the guy that we fixed becomes independent of one of its descendants, given some other guy in between. And these seem to be the only cases that you can get, apart from a slightly more complicated example, which I'm not going to introduce right now. Okay. So in all, yeah, and the key is that in all three of these graphs, there is an inequality constraint, right? So this one you all know, spells inequality. This one you get via an E separation, which again, Beata mentioned earlier. So we just delete the node T and we'll get this new joint conditional independence between X and W and Y. And here, this is a graph that Ellie calls the ghost, and he's shown that this also has an inequality in it. Okay, so then I'll sort of skip over this a bit because it's basically the same as the result I've already shown you. We just do the same thing now. We take the maximal ancestral projection and we'll show that that only makes the model bigger, but it preserves all the conditional independences. And therefore, any counterexample to the conjecture that is not maximal ancestral, but doesn't, and obviously it can't have any nested constraints, will have its maximal ancestral graph also as a counterexample. So maximal in this case just means that any pair of edges that aren't adjacent can be M separated by some other set of the observed variables. And ancestral, I already defined it, just means you can't be a adjoined by a bidirected edge to one of your own ancestors. Okay, and then again, very quickly running through this. So the first thing you need to do is to add edges from, so you consider pairs that can't be M separated in the graph. This is how you make sure it's maximal. And if one of them is an ancestor of the other, then you add a directed edge. And if it's not, then you add a bidirected edge. And then finally, you remove any bidirected edges between nodes that are already adjacent. And again, this isn't the way it was defined, but it ensures that when I do this, I can apply my proposition again and know that it's not going to change the marginal model that I have created by adding these edges. Okay, so here's a very brief example. This is the Verma graph we saw before, but I've added this edge W to Y now, so it only has the D separation between W and T. So I'm going to add an edge from X to Y because they can't be M separated, and V is an ancestor of, and X is an ancestor of Y. And then I'm not going to add any bidirected edges in this case, but then when I remove edges, I'm going to delete this bidirected edge because there's already a directed edge there. So, and I know that that's safe because of my proposition earlier. Okay, so why are mags sufficient? Well, this is basically the same slide as we saw before for marges. If we know there's no trivial nested constraint, then we can just project, and we know, we've just seen that you'll only make the model bigger and you will preserve all the equality constraints. So now we just need to consider mags. Okay, and then what we do is we look at the equivalence class of a set of mags, and it's not equivalent to a DAG if and only if there's an edge which is always bidirected in every single one of those graphs. Okay, if that happens, there can be two reasons for it. So the first is that we have a graph like this where both endpoints of the bidirected edge are involved in an unshielded collider. Okay, and this we know how to deal with because it's the bell graph, right? So we know that this does induce an inequality. And on the right-hand side here is the alternative, which is what's called a discriminating path. So it enables you to know that this is a collider, even though it's not unshielded, right? So there's this pair xt, but it does have an edge between it. So you can't just immediately read off that they are, this is a collider, but because of the pattern of the other edges, you can. And these are the only two situations in which you will get a bidirected edge. Yeah.
Sorry, what do you mean by always bidirected?
So I mean, so in a PAG, so I'm trying not to introduce PAGs because again, it's too many definitions, but basically in a PAG, you can always choose to orient all the edges which could be directed as being directed. And therefore the only ones that are left are just the bidirected ones that you started with. So that was what I meant by that.
It's not an edge between specific pairs. In the entire class of mags, which are ordinary Markov equivalent to G, there's just a bidirected edge between some pair in all of those mags.
No, so there is a specific pair that will have a bidirected edge between it in every graph.
Oh.
So like in this case, for example, it's clear that it must be because this has to be a collider and this has to be a collider. And therefore, any graph that is Markov equivalent to this will also have these both as colliders, and therefore this edge must be bidirected. Good question. Okay, and then, yeah, so this is just sort of...
You have 5 minutes, yeah?
5 minutes, okay, perfect. So we know that if you have a 4 chain of vertices with 2 unshielded colliders in it, then it's going to induce inequalities. This is the bell graph. This is the bell graph if you condition on W and X. And this, so you can, well, there's different things you could do, right? You could sort of condition on W and you'll end up with the triangle scenario, which again, we know induces inequalities. Okay. And for the discriminating paths, what's interesting, it doesn't matter how long the discriminating path is, we can just use E separation to show there's a constraint. So here we just delete x, and here we delete x and t. And if we had, a discriminating path of length k, we would just delete k minus 3 of the intermediate nodes. Was it k minus 2? I get confused. But yeah, so we just delete these guys, and then we find that there's an E separation. And it's non-trivial because this was not a D separation in the original graph, right? So if I condition on x, then I'm going to be dependent on z. But if I don't condition on x, I'm going to be dependent on y. So I can't have both of them jointly. Okay, so that shows that it's a non-trivial inequality that you get in addition to the equality constraints. Okay, so now we're done. We've shown that if a graph is a counterexample to the claim, then so is its maximal arid closure. If it has a non-trivial nested constraint, then it induces an inequality. If it doesn't have a nested constraint, then another counterexample will be the maximal ancestral closure of that graph. And if one of these graphs has a definite bidirected edge, then we show that that will also induce an inequality constraint, and then we're done. Right, so any graph that is not Markov equivalent to a DAG will fail at one of these stages. So briefly, so what I've tried to do is introduce this proof, which may be of little interest beyond for proving things like equivalence, which is something that does interest me. I sort of tried to introduce some ideas which might be of interest to people, right? So maximal arid projection, I'd say, is a very useful concept. And I've shown in another paper that, for example, if you have a graph which is not maximal or not arid, then there's always a pair, sorry, is not maximal, I should say, is there's always a pair of vertices that aren't adjacent that you can make identically equal and have all the other variables be independent of them. So if you imagine trying to do causal search with that, you just conclude that these two guys are adjacent and everything else is totally irrelevant. Whereas actually the structure you have to use is much more complicated than that. So there's something very nice about maximal arid projection because it's precisely the set of graphs where that cannot happen. I've also introduced nested constraints, then maximal ancestral projection and discriminating paths. So that's just sort of a way of orienting extra edges in a mag. And then I've sort of introduced E separation, although I guess Beata did that for me earlier today. And as I say, I think you could significantly simplify this proof if we understood the nested PAG better. So then we could just say, okay, we've got a maximal arid graph, and then hopefully there'll be a result which is similar where we say, okay, if it has a bidirected edge in every graph, then the edge will be bidirected in the nested PAG. And if we don't, then it's going to be Markov equivalent to a DAG. Okay. And then we'll be able to skip the ancestral projection part entirely. Thanks very much.
Questions?
I saw Rob Speckins online. It was saying that he was doing something.
Can I ask my question? Can you hear me?
Yeah.
Really nice talk. Thank you. I just was wondering, in your proof sketch, at some point you said there's generically 3 cases that give you a new independence.
Yeah.
And so should I understand that as this is kind of a classification of all non-trivial nested constraints, that it always boils down to these 3 structures?
So it's not quite true because you can get this tricky example, which I have prepared some slides on. So
sorry, I can't see your slides very well from just seeing a video of the room, but
okay, so can we sort of get back to
if
the slides?
Switch it to just showing the slides on the Zoom, that would be great. Thank you. Yes, it's done.
Excellent. Okay, so this is a graph where you get something a little bit different. And what's interesting about this is that this is also a MAG model, right? So, and And therefore you would think maybe the constraints are just the same. And what you see is it is a mag because, for example, W is marginally independent of Z, so there's a constraint there. And it's conditionally independent of T and Y given X, and W and X are conditionally independent of Y given T, and so on. So it's a maximal graph. But it turns out there is a nested constraint, which is something that surprised Thomas, because if you fix T, now you get a joint constraint between W and Z and Y given T. You just marginalize X and then no information can flow between them. So this is a sort of separate case, which I slid under the radar in some sense. But you can see in this case, you get a 5-chain. So it's even, there are even more obviously inequalities in this case. But yes, I think that for entirely new independences, nested independences, so that are revealed by a fixing, these are the only 3 sort of generic cases.
That's really interesting because it suggests a kind of classification, you know, by your theorem of where you expect to see inequalities.
Okay.
Just to be clear, you may have to go many levels down. It's not that these are necessarily after one fixing.
Yes, yeah, absolutely. So so this is just, you just think of these as cartoons, right? So there might be loads of other vertices that we've already fixed that I just haven't drawn on. And of course, there will be, you know, in general, this could be a whole path of vertices from T to Y and from W to X. And that's also fine.
Great, exciting stuff. Thanks.
More questions?
So maybe related to this. So after a number of fixing, you got this structure and you can show there is inequality. Does that imply there is inequality in the origin distribution just by?
Yes. So if you think about the nested model, there's no inequality, right? You just get the independence. Whereas this is clearly giving you something extra because it's on this final structure, which you would not get unless it were an additional thing.
Yeah, I'm just a bit worried because those things are on the margins.
Right, but the point is, in the nested model, you've got to some factor where there is no inequality. All the fixings you do will not induce any inequalities directly.
So just to be clear here, the nested model is that's sort of true by definition because nested model is being defined by the constraints.
Exactly, yeah. So it's defined by the independencies you get by doing fixings.
Yeah, I'm just a bit worried because in the DAG, if you just look at a specific margin, there could be inequalities, and you would call them as trivial inequalities.
Sure, but the point is, if we were doing this in a DAG, you would never you can fix anything, and you never induce any inequalities because all you do is add independences. Right, and so if you're doing valid fixings in the nested model, all you ever do is either nothing, you just introduce trivial inequalities because you fixed, or you get some new M separation, and that's the definition of the model.
Yeah. No more questions? Let's thank the 2 speakers.